All right, we're starting a new chapter dealing with circular motion, where instead of an object going in a straight line, it's to be held by a string or a force pulling it in, and it's not moving away from a particular point, so staying the same distance from that point around, creating the circle. That is called angular motion or circular motion. Now, we're going to pretty much mirror this with what we did with the linear one-dimensional motion. First we started with then was distance. We're going to start with displacement, which is technically the same thing, except now we're just figuring out the distance around the circle it's taking. Okay? So, what we're going to do is we're going to recall what a circumference is, how we find it. The circumference is the complete distance around the circle. Okay, so we have a circle here, and we have a point we've identified as the point at which the circle, the object going around the circle is heading. The distance then from that point to the circle, as you probably recall from geometry, is called radius. And so it's that constant radius that we have going around. Well, if it goes completely all the way around, the formula that we were taught in geometry is C equals 2 pi r, or pi times d. But since we're going to look in terms of the radius, we're going to ignore the diameter part, although I will caution you on some problems that will give you diameter, of which of course you'll have to take half of that in order to use it as the radius, which is the important part of this motion. Okay? Now, the distance here being the radius, if you measure that distance and take the same distance around the circle that's equal to that, let's say about right there, and let's say this distance from here to there is the same as the distance from here to there. So this would be equal to 1 radius. The problem that is, of course, that the radius is defined in terms of here, so they have to give that another name. So they drop the US and put AN. So this is equal to 1 radian. Or we'll symbolize that as RAD or rad, so 1 rad, rather than stands for radian. And so if we plug that in for this right here to find the distance around, and we replace R with 1 radian, that means then that the circumference is going to be equal to 2 pi times 1, which is 2 pi radians. So the circumference would be that. Now, another way to look at that is, instead of calling it a circumference, that can also be considered a complete revolution. And there's a lot of examples of that, but if you ever take a look at a tachometer in a car, which measures the rotational speed within the car system, that is measured in revolutions per minute, RPMs. So for this right here, if we were to consider that, then we would consider this equal to, this doesn't like that, equal to 1 revolution. So 1 revolution equals to 2 pi radians. Now, we also can measure distance around in degrees. And if you recall from your geometry days, that 1 revolution is equal to 360 degrees. So that means then that 360 degrees equals to 2 pi radians. And if I divide both sides by 2, then pi radians equals 180 degrees. And we're going to be able to use that relationship there as a conversion from radians to degrees or degrees to radians. Okay, so let's put all this together and let's come up with some examples that we can use this in, and then I'll give you a practice problem. So let's suppose you have 0.667 radians around the circle, and you want to know how many degrees that is. So you take 0.667 radians times fraction line, and we're going to put radians on the bottom and degrees on top. I'll just use a little degrees in there because I'm going to put a number in front of it. And the relation we found in the previous page there was for every pi radians, we had 100 degrees. So the radians cancel out, and we multiply this out, and we get 38.2 degrees. Okay? And let's go the other direction. Let's suppose we start with 240 degrees, and I want to know how many radians that is. Okay, same thing. 240 degrees times fraction line. And we're going to put degrees on the bottom and radians on top. We're going to use the same relationship only now it's going to be flipped. Because we're going to put 180 degrees on the bottom and with the degrees and the pi with the radians. Now there's two ways we can give this answer. One, if you want to leave it in fractional form, which you see a lot of in various situations. You cancel a 60 out of both of these, and that's going to give you a 4 here and a 3 here. So your answer is going to be 4 pi over 3 or 4/3 pi radians. Now if you do the calculator work on that, it won't give you 4 pi over 3 or 4 pi. Instead, it's going to give you 4.19 radians. Anyone, it's not radians. Any one of these answers is correct. Okay? Let's take another example. Let's suppose that we have 2.5 revolutions, which we're abbreviate REV, and I want to know how many radians that is, and I want to know how many degrees that is. So I'll do the 2.5 revolutions equal how many radians there are. So 2.5 revolutions times, and one complete revolution, well first of all, let's get the labels cancel out. Revolutions on bottom and radians on top. And for every one revolution, we define that as 2 pi radians. We'll multiply that across to get 5 pi radians, which is an acceptable answer, but if you use the calculator, multiply 5 times pi, and you get 15.7 radians. Do the same thing with the degrees, 2.5 radians, or revolutions rather, times revolutions on the bottom, we'll put degrees on top, and one revolution represents 360 degrees. We multiply this out, and your answer is 900 degrees. So this is all about converting between straight line and angular or circular motion, or measurements. Okay, your assignment, page 260, 4, 6, and 8. Have fun.